Now we come to the first speaker of the day, Moritz Wiese. He studied math in Bonn, and then did his PhD with Holger Boche, first in Berlin and then in Munich. He has since studied classical information theory from various directions, but with a focus on security. And recent work, which he will also show, has also led to implementations for wireless communication systems. So we can here observe by example how to transition some theoretical concepts into actual implementation. And I hope that this makes a perfect start for the day. Welcome, Moritz. Stage is yours.
Because my talk consists of two parts, theory and practice. And so theory is nothing new, really, I would say. So I introduced two, the two basic models of information theoretic security, classical information theoretic security. I'll just talk about how to measure security and give a little comparison of these two basic models. In the situation where one wants to transmit messages securely. And then the practice part is about like a sequence of implementations we've done. I mean, basically with me as the theoretical advisor and with people who actually know how to deal with hardware from our group. Yeah, so the first of these two models I mentioned is the classical wiretap channel. So that means we have three parties, Alice, Bob, and Eve. Alice wants to send a message to Bob reliably, in the sense that Bob decodes the message with high probability, and Eve is an eavesdropper who should not be able to understand the message. And these channels between from Alice to Bob and Alice to Eve are noisy channels, meaning when Alice inputs something to her channel, then it's not exactly sure what Bob will obtain or Eve, but an input at Alice's side will just determine a probability distribution of the outputs at Bob and at Eve's side. And I suppose, so yeah, you know, I don't mention any analogies with quantum, I've decided, but in this case, I think you can, you know, yeah, whatever. I don't. Okay, so yeah, and now our goal is, of course, in cryptography, that basically this problem, or I guess the cryptographers consider this problem solved, but we would like to solve this problem of confidential transmission differently. We don't want to. We don't assume that Alice and Bob share a secret in some way. So in classical cryptography, you would assume that Alice and Bob share a secret key, for example. And here we only want to use that the channel from Alice to Bob is noisy and that the channel from Alice to Eve is noisy. Okay. And now, of course, the first thing one observes is that if the channel from Alice to Bob is noisy, then Bob will have to do will have to deal with the noise, right? And in such a way that he can still decode the message. So if the noise on Bob's channel is the same statistically as the noise on Eve's channel, then we won't obtain security, because if Eve does exactly the same as Bob, she can also decode the message. So there has to be a difference in the noise levels, let's say, yeah? So we can't always solve this problem satisfactorily in the sense that we can transmit something, yeah? That is, yeah, the disadvantage compared with cryptography if we don't want to use any secret key. Okay. And that's also the main disadvantage practically, because you need to know something about the noise to the eavesdropper channel. So you need to model you need to have a non-trivial model for the eavesdropper, and that's a certain restriction. And yeah, not in every situation can you make sure that this eavesdropper really satisfies these restrictions. And if it doesn't, and you try to transmit anyway, then you don't have any security. Okay. Second model is somewhat related, but still different. So here the goal is not to transmit a message, but to generate a secret key. So this is more or less, I guess, the classical analogon to a quantum key distribution. So yeah, we have a source which emits something, symbols you can observe. Alice observes something, Bob observes something, and Eve. And what they observe is correlated, but not the same. And the goal is that Alice and Bob generate a key which Eve doesn't know. And this key should be uniformly distributed and secret. And Bob and Alice may discuss publicly. So they also have a noiseless channel, with perfect communication. But it's public in the sense that Eve can also, understands anything either Bob or Alice say. And here again, of course, if Eve's observations of the source are the same as Alice's, for example, then we won't get any security. We again have to require that there are some differences in the not the noise, in the source statistics, or in the statistics of the observations of Eve from those of Alice and of Bob. Yeah. Okay. So now the first thing I want to talk about is how we measure security here. Well, I said secrecy because security, of course, can be understood in quite a lot of senses. So here's secrecy. So I introduce a few symbols. So the secret I will always call M, even if it's a key. M for message. The eavesdropper's observation will be called Z. Then, like I said, everything's basically statistically, so we need to talk about the statistics of M and Z. And so we have a joint distribution of the secret and of the eavesdropper's observation of the secret. P, M, Z, and with the marginal distributions PM and PZ, and those are classical probability distributions. Okay, so the ideal situation is perfect secrecy. Perfect secrecy means that the secret and the eavesdropper's observation are stochastically independent. So whatever the eavesdropper observes has, statistically speaking, nothing to do with the secret. In other words, one can say that the conditional distribution of the observation given the secret is independent of the secret. And I guess one point I want to make here is that we will, when we have established a system, then we assume that this kind of is fixed, so we have a mechanism, a code for transmitting messages, and this is fixed, and then we can plug in various differing secret distributions, okay? And this becomes important here in these measures for quantifying secrecy, because perfect secrecy in general is unattainable, right? So this is, let's say, the perfect situation, and unfortunately perfection is not always obtainable or at too high a price. So we want this equality, or this relation, not to hold with equality necessarily, but like with almost equality. And this almost has to be measured in some way. So we can measure this using some kind of metric, D. Assuming that this metric is 0 when both entries are equal, then we would want let's say we want the distance between the product measure of M and Z and the joint distribution to be small. And this can be done either in a way that we fix a distribution of the secret, or that we consider something like a worst case secrecy measure, where we maximize overall possible secret distributions. Yeah? And that's called semantic secrecy. Right. And so what does this mean? One could ask, okay, this is kind of the abstract way of measuring security there, but you know, this D is not specified yet. And the question is, for example, now from a practical point of view, what should small mean, right? What is a good what would a good epsilon be, right? So we need to think about what this quantity means. And for that, of course, it is crucial to fix such a metric. And yeah, the easiest thing for which to, or the easiest metric for which to derive an operational meaning of secrecy is the total variation distance. So this basically, one could say, measures the L1 distance between two probability distributions if you know they are discrete and you consider these probability distributions as vectors. And then we have this nice operational meaning. So these tildes here, they mean differs by at most a factor of 2. This semantic security means that, or can be interpreted in 2 ways, let's say. So the first one, this upper formula, means we can take any 2 messages or any 2 secrets, yeah. Then the adversary can choose any algorithm, and using this algorithm, the adversary wants to distinguish secret 1 from secret 2. Okay, so he knows exactly, yeah. So we choose one of these 2 secrets with probability 1/2. We send it, let's say, through this yeah, okay, I call it channel, right? So we let the eavesdropper observe what happens when we send this chosen secret, and then the eavesdropper can try to find the right message or the right secret. And yeah, his probability of finding the true secret should be approximately 1/2. So you know, his best algorithm for distinction should not be much better than guessing. And the second formula means basically that the adversary should not be able to compute any function of the message, no matter what the message distribution is. So this means whenever he applies any algorithm to his observation to compute this function, it should not be much better, or should only be negligibly better than if he tries to compute the function without observing anything at all, right? And if the best thing you can do with an observation is not much better than without observing anything, that's also considered to be secure. And these things are, yeah, equivalent. Yeah. So these 2 measures, they have analogies in cryptography. Although in cryptography, this adversary or the algorithms the adversary can use are computationally restricted a bit. But apart from that, this is basically analogous. So that's an interesting observation first made in this paper here, which is an interesting collaboration between an information theorist and two cryptographers. And okay, so this was basically this worst case kind of security. And for strong secrecy, where we fix the distribution of the secret, yeah, basically you fix this distribution, meaning you would not take the worst case messages, but you would average over them according to this given distribution. Okay, little comparison between cryptography and wiretap channel. So in cryptography, so this is now, yeah, made for the situation of the wiretap channel. I don't know if in the next talk we see something that sounded a bit like, yeah, okay, I don't know, it sounded like cryptographic secret key generation or something like that, if I got it right. So this is wiretap channel. Because it makes the comparison easier, and I know the wiretap channel better than secret key generation. So what's the difference here between the two things? So in cryptography, Bob and Eve may see the same ciphertext produced by Alice, right? This, like I said, this must not be in information security. In cryptography, on the other hand, Alice and Bob need to share a secret. I mean, even if it's if you do public key cryptography, someone has to know something which Eve doesn't, and yeah, right, because of course, otherwise Eve could just decode the ciphertext like Bob. And this is not necessarily not necessary in the wiretap channel. In cryptography, on the other hand, Eve has to be computationally bounded to make this practical. In the wiretap channel, that is not necessary. So these previous security measures don't assume any restrictions in terms of computational power on Eve. And then the question is, if in cryptography you can, I mean, yeah, you need some assumptions before you can start with the proof, right? And you assumptions on the computational hardness of the solution of certain problems. And yeah, that also is not necessary in the wiretap channel. On the other hand, of course, like I also said, we need some information about Eve's noise statistics. And that's basically the main disadvantage, I suppose, of this information security. Okay, so now how do we achieve this security on the wiretap channel, if it's possible at all? Well, one has to do some coding, and of course one has to do two things. First of all, like if there is noise on the channel from Alice to Bob, we need to do something. Okay, unfortunately we called it coding layer. So the coding layer means that we make this main channel from Alice to Bob reliable. And when we do that, we can completely ignore security. And then on the outside, we can add a security layer on the encoding and on the decoding side, which takes care of security. If you look at that, so assuming this blue block here is the set of all code words which can be sent from Alice to Bob reliably, meaning that, yeah, Alice chooses one of these code words and Bob observes what comes out of the channel and can with high probability tell exactly which of the code words Alice sent. And then in order to achieve secrecy, you need to do the following. You need to partition. So for example, if you have 8 secret messages to transmit, you partition this code book into 8 equal size subsets. And when Alice, for example, wants to send 000, she randomly chooses one of the code books corresponding to the subset of the code book, then sends that, and Bob can, of course, then decode this code book, and he knows to which subset this belongs, and also knows the message. And if you do this suitably, then Eve, together with the noise on Eve's channel, Eve will not be able to understand anything, and the security measures will be satisfied. Now, in order to, so I said there is some connection between the write-up channel and secret key generation. And I think the easiest type of connection would be the following. So assume all this rectangle here in all colors is everything that Alice can observe from the source, right? And then, I mean, everything has to be done suitably, right? So suitably, you can partition the whole observation space of Alice into these different colored blocks. And you interpret these differently colored blocks as codes for the wiretap channel, which basically gives Bob's observations and Eve's observations conditioned on Alice's observations. And then Alice can do wiretap coding on each of these sub blocks, on the blue one, on the green one, on the reddish one, and all the ones in between. And then, then basically you have the same type of secrets of keys, basically, that you generate for each of these sub blocks. So one can ask now, is there any, so can we quantify the connection between these two models? And for that, we need to look at capacities. So capacity would mean the maximum number of messages you can transmit, or the maximum number of, number of different keys you can generate. So more precisely, in the wiretap channel, you can look at the number of reliable secret message bits you can transmit through the wiretap channel, normalized by the number of channel users. So, you know, in coding, you use the channel several times. So you divide by the number of channel users. For the secret key generation capacity, you look at the number of secret uniformly random key bits you can generate, normalized by the number of observations of the source you have to make. And with this previous analogy on the two slides before, we have an interesting connection. So if this public discussion is not really a discussion, but only Alice sends something to Bob, then and if Alice can send anything to Bob, whatever she likes, right? So there's no rate limitation. Then the wiretap capacity is equal to the secret key generation capacity. On the other hand, if you introduce rate limitations, or if also Bob can retransmit something to Alice and so on, then both, you know, the two quantities can be larger or smaller in more or less arbitrary ways. And interestingly, also, if you allow real discussion in both directions, then a big advantage, I suppose, of secret key generation is that this capacity may be positive when the wiretap capacity is 0. So even if the noise is such, that basically at first, in the unidirectional setting, no secret transmission is possible. By sufficient discussion, you can make this capacity positive. I wanted to compare the wiretap channel and the secret key generation model a bit. So assume we want to transmit n uniformly distributed messages. One can use either the wiretap channel, or one can use the secret. One can try to use the secret key. Okay. So for the wiretap channel, what would we do? We observe the n message bits we want to transmit. Then we can encode them into n divided by c. This is the wiretap channel capacity, many symbols, and transmit those over the wiretap channel and decode. For the secret key generation, this is a bit different. So again, we want to transmit n uniformly distributed bits. then the idea would be to use the one-time pad, which is an idea from Claude Shannon. And this says that if we have n uniformly distributed bits and we want to encode them and encrypt them with n secret bits, then the XOR sum of these two sequences, or any other way for encoding this M sequence by the K sequence, is perfectly secret if and only if these secret bits are uniformly distributed. So that means we have to generate a certain number of uniformly distributed secret key bits. So to transmit our n bits, well, we observe the bits, then we have to observe n divided by secret key capacity, many source bits. We do the public discussion and all that's necessary for generating the key. And in this way, we generate n uniformly distributed secret key bits. Then we do the one-time pad and transmit this result to a Bob who knows the key again and can decrypt and understands the message. So it's a bit, one has to do a bit more, but on the other hand, like I said before, the secret key capacity might be larger than the write-up capacity. So it's kind of a trade-off. Okay, for practice, well, we implemented this modular scheme, like I said, using some security layer, which kind of a universal hash function based. I don't know, in case you know that, what that is. And for this type of security layer, unfortunately, one needs some seed over which one averages, but that's no secret key because Eve also is allowed to know that. So here I just need to introduce the parameters because they appear on the result slides, which come next. So the message has K bits. The output of the security layer has L bits. So that is basically what the L will be larger than K, and L minus K kind of quantifies the rate loss we have by introducing the security. And then we encode this into n complex symbols. Okay, and this is done as follows. So we implement this in hardware and simulate a channel with Gaussian noise. So you input the symbol and you add Gaussian noise on it. And for this, we used so-called software-defined radios, which basically can generate symbols, analog symbols, which you can input to antenna, for example, but they have some software components you can program them, right? So it's good for research, for example. And exactly, so this channel, this was no real wireless transmission, but it was generated by a signal generator, this SMW thing up there. And then we have an Bob receiver and an Eve receiver. And we got the following results. So this DER is the error rate of Eve. Yeah, it should be roughly 1/2. This about more or less guessing type of quantity. This BLER, B-L-E-R, is not so interesting because this just gives the decoding rate if Eve does basically the same thing as Bob, like uses a normal decoder. So this doesn't really have too much to do with security. And we see how this DER decreases with an improving channel quality. So this SNRE means or indicates the channel quality for Eve, and the channel quality increases if this SNR increases. So we see, yeah, nice. We really get security if Eve's channel is bad enough. Then we asked ourselves, now if we want to sell this to network operators, telecom, for example, they might say, but doesn't this take too much time, adding this security block and the encoding on the decoding side? And basically, the latency that is introduced by doing this depends on the complexity of the security layer. And we noticed that, well, the complexity or the latency introduced is still small, even if, so it depends a little bit on the length of the message, right? So I think so the difference between dashed and solid is the latency. I think for the red curves, we had k equal to 4, so quite a short message. And for blue, we had k equal to 40, so meaning 40 bits per transmission would introduce something like 8 microseconds. In this implementation, I mean, of course, certainly can certainly be improved. And we also had a look at security when the channel fades, meaning that the channel states or that the channel quality basically also doesn't only depend on the noise, but also on the situation. If you're in a car driving through a big city, or if you're in the countryside where there are only trees, yeah, or cows. And so this RMA means rural microcell, UMA means urban, so that is the urban scenario. And there we see, well, okay, and this type of channels that were used to model these situations, they're basically standardized, and so standardized in the 5G standard, in this standard that governs our cell phones. And so you see that, okay, basically the rural scenario is a bit better than the urban one, but still they are comparable in terms of when the parameters are the same. Yeah, and you see, I mean, in this situation, L minus K equal to 0, that means we don't have any security, right? So we just transmit things, and there we see nicely that Eve has a dramatically, I would say, better performance in the sense that she can really distinguish messages compared to where we do add some security. And yes, that's almost all I wanted to say. What do I want to say here? Basically, what I suppose the interesting thing for you might be that we basically also, so this is actually something, something real, some real wireless transmissions, which we did in our lab. And you can see, so basically, if you have several antennas, you can kind of direct in which direction the power is sent. Yeah, and you can see that, yeah, actually the quality of each channel does depend on the direction in which you send your messages, basically. So that's, I suppose, the main message here. And if you want to see such a system in reality, just go to Berlin next year, and there's the 6G already, yeah, 6G, sorry, conference, and there we present all that stuff. Yeah. Okay, that's all I want to say. Thank you.
Thanks for your fine presentation. Is there any question or comment?
Okay, yeah, that was quite impressive. I mean, this line, from Cesar Körner until fading channels. So I noted down a couple of questions, but the first that came to my mind is, since you compared the latency, or you analyzed the latency, did you also compare this to a PQC implementation?
No.
Ah, okay.
We just compared with or without. I mean, with PQC, I suppose. I mean, the thing with this latency comparisons always is that it depends a lot on the quality of the implementation, right? If you do it in hardware and software, and how good you do it, how well you do it. So, I know. I mean, I think all our implementations, they are not I suppose, optimize too heavily.
Yeah. Okay, so there's some very interesting work left to do. Yeah.
There's also a question from Zoom. Perhaps pinch in. Can you unmute and then you can ask by yourself?
Yes, thank you, Moritz, for your presentation. So I have two simple questions. So first, that is about the design of the number of seed bits, because by, for example, the level over hash lemma, then we may, there are different versions of that. We may use mean entropy or epsilon, the smooth mean entropy, or other kinds, for example, by Tiagi and he has a version bound that by just mutual information. So I would like to know which kind of metric you use to measure the number of seed bits, that is to design the hash function.
Yeah. So the number of seed bits you need, basically it is 1. So you don't really need any seed if you know exactly what the channel is. On the other hand, first of all, introducing certain kinds of universal hash function makes the analysis simpler and also adds robustness. So the channel can vary a bit and you can still use the same scheme. But I don't have any trade-off between, generality of applicability or, robustness, let's say, versus seed length. For a fixed channel, like I said, you don't need any seed really, or just 1.
So I have a small technical question that you'll be able to answer right away, and maybe a larger question that might be something to think about. Question 1, to implement all these physical layer security schemes on the software-defined radios, I see ETUs over there. Did you have to reprogram the FPGAs, or were you able to do everything within the software stack that's given by the radios? And by you, I guess I mean your postdocs and students and you. So
I don't know.
You don't know?
No.
All right.
No, I don't know. No.
The second question is, since this is a entanglement-assisted communications workshop, so I like these experimental studies because I'm conducting one myself right now using similar radios on a different notion of security, and it's informing us about the protocols one needs to use for establishing quantum secure communications. So because there's a lot of things that have to happen on the background when you actually stuff that us theorists kind of cast aside. Radios have to be synchronized, for instance, at several levels. They have to have location information at times. They have to have signal strength information. They have to have a way to resynchronize their carriers every once in a while because those fall out of sync. So what can you tell us, the folks who are doing research mostly on quantum security, of the lessons that we can learn from your experiments when we attempt to bring our work forward into the actual implementation domain?
Well, I know nothing about hardware, but I know the others had quite a lot of work to do. And did I show something like this synchronization? They had a clock also to synchronize everything. And I think, of course, that caused a few problems. I mean, just getting it running. So unfortunately, I can't really tell you much about what now follows from this for quantum, except that it's not straightforward, I think.
I could see down in the references that you are using a type of semantic security as your target. Are you using the semantic security definition from cryptography? And are there ways with your type of methods to go beyond semantic security?
So what we use is not semantic, it's also called semantic security. It's not the cryptographic one, because I mean, it's also called semantic security because of this analogy, right? So there's here. So here, this really, I mean, okay, this maximization is not, I didn't formulate exactly what you maximize over, but it's any kind of, so this is basically what the adversary can do, right? And this is anything, any mathematical transformation function that you can use. And I think in cryptography, there are always some computational limitations which are assumed, as far as I know, and then exactly. That's the difference. And so in cryptography, you don't end up with this nice total variation distance.
To me, as a cryptographer, the main difference between semantic security and stronger notions of security is this idea of adaptability. So providing security even against man-in-the-middle attacks and against attackers who can keep querying like your oracle. And this sounds like something that's more close to like semantic security as it's used in cryptography with targeting passive attacks.
In that sense, yes, I think you're right. So this is just the models that are showed on the first slide. So no man in the middle, no other things that come additionally from the outside.
Okay, thanks. So maybe a quick question, because we don't have much time, I think. So previously I heard that the problem with wiretap channel coding is that there are not that many good codes that provide both encryption and error correction. But in your scheme, it seems that these two things, secrecy and error correction, are somewhat separated. And well, we do possess excellent codes for error correction, such as LDPC or turbo codes. So my question is, do you use such, Shannon approaching?
We used
error correction.
Polar codes.
So polar, okay.
Yeah, exactly.
Thanks.
So yeah, I would, in principle, I don't really agree with this statement that there are no real good wiretap codes. So that's at least not any longer true. The thing is that the wiretap channel itself is the problem, not the code. And in coding, like I said, you don't need to think of security when you do the reliability coding. So you can use what you like best.
So thanks again for your fine presentation.